Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi again, everybody. I am your Madam Ruby. We are going to continue our lesson 16 of chapter 3, atomic structure. Before this, we've learned how to draw the orbitals of electron. But today we're going to learn how does electron takes up their position in the particular orbital, and is there any rules regarding their positions? Before we learn about the rules, we need to write the electronic configuration using as PDF notation and orbital diagram. Then we would try to understand Hund's rule, Pauli exclusion principles, and Aufbau principle in filling the electrons in the orbital. We also need to write the electronic configuration for monoatomic ion, and we want to explain the anomalous electronic configuration of chromium and copper. What is electron configuration? Electronic configuration is showing how electron is filled in an orbital. It will describe the arrangement of electron in an atom, and we can use as PDF notation, electronic notation as the same meaning as electronic configuration. We must follow three rules. Aufbau principle states that electron in an atom should be filled in an orbital in order of increasing energy. So the electron will be occupying the orbital with the lowest energy first, whereby each orbital will occupy only 2 electrons. For example, the lowest orbital is 1s. For sodium, it has 11 electrons. The first 2 electrons would be situated at 1s. Another 2 electrons would be situated in 2s. And then 2 times 3 is 6. 6 will be occupied at the 2p orbital. That would be 6 plus 4, 10. Another one, 1 electron would be at orbital 3s. So here we go. We already fill in the electrons according to the lowest energy level first. The lowest is 1s, followed by 2s, followed by 2p, and the last electron is at 3s. This is for sodium atom, which has 11 electrons. The order in which atomic subshells are filled in an atom start with the 1s orbital, and it will move downward following the arrows. So you can see here 1s is the first one, and then followed by 2s, followed by 2p, and then followed by 3s, followed by 3p, and 4s, and so on. Now let's look at the electronic configuration of titanium, Ti. It has the proton number 22, so it has the number of electron 22. Basically, we want to put the 2 electrons in orbital 1s first. Okay, there you go. And then you want to put the second 2 electrons in the orbital 2s. Next, we are going to put it in the orbital 2p. P has 3 orbitals, x, y, and z. So it would be 2 electrons each. That is how you put the electron upward first and then downwards in pair. And then after that, 3s occupying 2 electrons, and 3p also occupying 1, 2, 3, 4, 5, 6 electrons. How many do we have already? This is 2, this is 8, 10, this is 2 and 6, 18. So 4s would make it 20, and we have another 2 that would occupy the 3D orbitals. So how are we going to put the 2? One, the arrow going upward, and another one on the second orbital, the arrow going upward also. So here you go, the electronic configuration of a transition element, titanium. For transition element, it is noted that 3D orbital will be filled partially. So we need to learn about the rules carefully. 4s is more stable than 3D orbital in terms of energy. But as soon as the electron occupy the 3D orbitals, 4s electrons are repelled to higher energy. For titanium, again, we revise the electronic configuration is as shown. The electron valence is 4s2 and 3d2. This is when we apply Aufbau Principles, stating that we have to fill in the lower energy level first. But once the 4s is filled and 3d is filled, 4s is repelled to higher energy. So, due to the energy level, now we can write down 3d2 first. And then we write 4s2. Both configurations can actually be used at any time in our studies. No worries about that. The second rule that we have to learn is Hund's rule. The situation for Hund's rule is when we have the same energy level for the orbital. We call this orbital degenerate orbital. It has the same energy level. For example, 2p and 3p, they have 3 orbitals of the same energy level. For example, when we put electrons in 2p and 3p of titanium just now, they were put singly arranged in the same spin first. There are three orbitals over here. So we put 1 upwards, 2 upwards, and 3 upward first. Because the most stable arrangement of electrons in subshell is the one with the greatest number of same spin. So if we have enough electron, we will pair them. We will pair the electron and the arrow will go downward. 1, and then 2, and then 3. This is how we fill in the orbitals with the same energy level. Hund's rule is applied where orbitals of equal energy are available. For example, 2px, 2py, and 2pz. This orbital is called degenerate orbitals. Each of these orbitals will be first filled with 1 electrons with same spin. And then, when all the orbitals is filled with that 1 same spin, then it will be added with the second electron with opposite spin. Okay. For example, let's look at carbon. This is more simpler example compared to titanium just now. The first electron, the second electron, the third electron, the fourth electron. This is 1s and 2s. But for 2p, the second electron is not put at the first orbital, but it was put at the second orbital, same spin. Let's look at nitrogen. Nitrogen has 7 electrons, so we add another electron here at a degenerate orbital of 2p. Same spin going upward. The next one is oxygen. Oxygen has 8 electrons, so where is the next electron will be? There you go, at the first orbital of 2p, and the spin is an opposite one, so now it becomes a pair. The next one is fluorine. We add 1 electron at the second orbital of the opposite spin. And finally, neon has 10 electrons, and the last electron will be put oppositely at the last third 2p orbital. Okay, given also is the electronic configuration for C, N, O, F, and neon. I would always like to sing 1s2, 2s2, 2p6 for my students, just for fun. Let's do a simple example of oxygen, which has the proton number 8, meaning that it has 8 electrons. The electronic configuration is 1s2, 2s2, 2p4. So 4 plus 4, it has 8 electrons. The first 2 electrons will be filled in orbital 1s, which has the lowest energy level. The third and the fourth electron will be filled in the orbital 2s. And the last 4 electrons will be filled singly first. 1, 2, 3 in each orbital of 2p. And the last electron, the 8th electron, will be placed in a pair with the first orbital of 2p in an opposite spin. That's how you arrange the electrons according to Hund's rule. Let's consider carbon, which has the electronic configuration 1s2, 2s2, 2p2. Different ways of distributing 2 electrons among 3p orbitals are, on the left, 2 electrons in one orbital. In the middle, 2 electrons in different orbital. And on the right, 1 electron for one orbital, and that electron has the same spin. Which one is correct? Think about it. Did you get it already? Yes, the answer is the right one. According to Hund's rule, the electron must be arranged in a single orbital first on the same spin. Well done. The third rule is Pauli exclusion principle. Pauli states that there are no 2 electrons in an atom that can have the same 4 quantum numbers. It cannot have the same set of N, L, M, S values. For example, helium has 2 electrons. So the set of quantum numbers for electron in helium would be 1, 0, 0, positive half. And another set would be 1, 0, 0, and negative half. According to Pauli exclusion principle, there will be no 2 electrons that can have the same 4 quantum numbers. For example, helium, the first electron, the spin is going upward. The second electron would have an opposite spin, like the right ones here. So you can see that the number of the electron is now different when it has a different spin. How do we write electronic configuration? These are the procedures. Firstly, we need to determine the number of electrons for that particular element. And then we have to add the electrons in subshells or in orbitals according to the increase of energy level. This is following the Aufbau Principles. Then we have to use Pauli exclusion principles, whereby there will be no more than 2 electrons in an orbital, and the 2 electrons must have opposite spins. Lastly, we apply Hund's rule. Orbitals in a subshell are singly occupied whenever possible, and all unpaired electrons have the same spin direction. Let's do example 3.5 in your page 95. These are the questions, and let's do it one by one. The first question is, write the electronic configuration of sodium. Sodium has 11 electrons, so the electronic configuration is 1s2, 2s2, 2p6, 3s1. It has only 1 electron valence. Second question, draw the orbital diagram of sodium atom. Orbital diagram is boxes that represents the orbitals. So you draw a box and you label the box 1s, that is for orbital 1s. So you draw the electron, a pair of electron with opposite spin, that is the 2 electron in each orbital. The last electron, the electron valence, would be not paired because it's only 1 in the orbital 3s. Okay. The third question, write the SPDF notation for the valence electron in Na atom and draw its orbital diagram. The valence shell of N is equals to 3. The SPDF notation is 3s1. The orbital diagram of the valence electron is shown on the slide. This is it. Question 4. Draw the shapes of orbital occupied by the valence electron in sodium atom. As we have known, the valence electron for sodium is only 1 electron. So we need to draw the shape. We have learned this in previous lesson. So let's just draw the y-axis. This is z-axis. This is x-axis. And we label first, this is 3s orbital. And 3s is a spherical shape, like the ones we have here. So there you are, the shape of orbital 3s that is occupied by the valence electron of sodium. Next question is, write a set of quantum number for the 7th electron in sodium atom. So here we need to know which electron is electron number 7. So we calculate the electron for sodium. This is number 1 and 2. This is number 3 and 4. This is number 5 and 6. This is number 7 and 8 and 9 and 10. So number 7 would be here. So the quantum number would be n equals to 2 because it's 2p, L equals to 1 because it's p, M equals to either -1, 0, or +1 because -1 may refer to X, Y, or Z. Spin, it can be the upper arrow or the lower arrow. So for this question, it can have up until 6 choices. Next question is, write electronic configuration of sodium ion and draw its orbital diagram. We know that sodium ion, the formula is Na+ because 1 electron moves out. So the number of electron is only 10. The electronic configuration is 1s2, 2s2, 2p6. Here, you can see that the orbital diagram is shown at the bottom of the slide. We have shown to you how to draw the shapes of orbital S and P in the previous lesson. So, since sodium ion has the orbital of 1s, 2s, and 2p, you have to draw all the orbitals. 1s is a bit smaller, 2s is bigger than 1s, and then 2p, y, x, and z in their correct orientations. You have to draw it all and you'll be given 1, 2, 3, 4, 5 marks. Next, we are going to learn about exception to the Aufbau Principles. Electronic configuration of chromium and copper has been established by experiment, and it was found that they are not the configurations that follows the Aufbau Principles. Why is that so? First, let's look at chromium. The electronic configuration is Ar. This is abbreviated to noble gas. And the valence is 3d4, 4s2. It is what we expect because electron will fill in the lower energy level first, 4s2, and then 3d4. But what we observed in the experiment is that the electron fills in 3d5 and then 4s1. 3d5 is filled in by 5 electrons. It is half filled, and 4s1 is filled with half electron as well. 4s1 is also half filled. And what about copper? Copper has 29 electrons. The electronic configuration is Ar, 3d9, 4s2. So we should expect the electron fill in 4s2 first before filling in 3d9. But here, the observed electronic configuration from the experiment stating that the electron fill in the 3d orbitals fully first before filling in the 4s orbital. So if you can see, the half-filled orbital of chromium and the fully filled orbital of copper is more stable than the partially filled orbital, which is expected from the Aufbau Principles. Yes, half-filled or fully filled orbital is more stable than partially filled orbital. For example, copper, it should have 3d9, 4s2. But actually, when we look at the experiment, the data given to us is electron is filling the 3d first. So it is 3d10 and 4s1. So it is found that fully filled orbital for copper is more stable than partially filled orbitals. Besides chromium and copper, other elements with anomalous electronic configurations are niobium, molybdenum, ruthenium, rhodium, silver, palladium, platinum, and gold. Alhamdulillah, we have finished chapter 3. We have learned how to write SPDF notation using Hund's, Pauli, and Aufbau principle by stating the electronic configuration of monoatomic ion and explaining the anomalous electronic configuration of chromium and copper. See you again for the continuation of General Chemistry Tamhidi in chapter 4. Bye. Assalamualaikum warahmatullahi wabarakatuh.